So in this lesson, we are going to continue talking about finding rational zeros, or in other words, solving polynomials. And you can see that we have one goal with two sub-objectives. Our goal is to find all the rational zeros of any polynomial I give you, first by using a graph, and then by the guessing and checking method. How can I use a graph to solve polynomials? Well, we need to remember a couple of important ideas. Number one, another name for solutions when you solve a polynomial is zeros. Right? I've been using this term a lot. Hey, this is the zero of the polynomial. Find the zeros of the polynomial. The reason why we call them zeros, so another name for solution is zeros, because a solution is any value, and we're talking about x value, any value that makes the equation equal to zero, right? That's literally the term of why x values are called zeros, is because it makes the whole function equal to zero. Graphically, solutions to polynomials are x-intercepts. Right. So that's the key idea, that if I have a graph of any equation, we're talking about polynomials now, but it could really be any function that you'll face in your entire mathematical career, that if you were to find the x-intercepts, those are the zeros. Those are the solutions to the equation when you set it equal to zero. So for example, right, if I have the function f of x equals x squared plus 6x plus 8, and we were to graph them, right? So let's just do a quick review of graphing. I want to find the x coordinate of the vertex. So it's negative b in this case is 6, negative b over 2a, which is negative 3, and then make my xy table. So let's say I had, I don't know, negative 3, negative 4, negative 5, and I were to plug these guys in. So plug in a negative 3, you're going to get a, what's that? That's going to give you a 9 minus 18 is a negative 9, so that's a negative 1. Plug in a negative 4, you get a 0. Plug in a negative 5, you get a 25 minus 30. Let's see, 25 minus 30 is negative 5, plus 8 is a 3. Right? Wow, that took me a while. So then you go ahead and graph this guy. So got some pretty big negative values, so make some tick marks negative. So let's plot negative 3 comma negative 1, negative 4 comma 0, negative 4 comma 0 here, went wrong direction, and negative 5 comma 3. And of course we can mirror image it to the other side here. So for this function, this parabola, this is the shape we get. Now we should easily be able to see what the x-intercepts are. We can see that the x-intercepts are located at negative 4, or x equals negative 4, and x equals negative 2. So I would say negative 4 and negative 2 are the zeros of this function. They are the x values that, when you plug them in, would make the whole equation equal to 0. So if we were to solve solve this problem, x squared plus 6x plus 8 equals 0. This is a quadratic equation. Solve it by however you want, factoring, completing the square, etc., etc. Well, it turns out that this guy is factorable, x plus 4, x plus 2, and you get x equals negative 4, x equals negative 2, right? So you can see how we get the same answers. So that's basically what this quick demonstration shows, that if you have a graph of a function and you were asked to solve it, find the zeros, you're really looking for the x-intercepts. So that's pretty simple, right? If I ask you to solve, just look for the x-intercepts that are easily readable. So for example, suppose I asked you to find all rational zeros of f of x equals 4x cubed minus 20x plus 16, and they will give you a graph. Now, obviously in your practice, you'll have a computer-generated graph. I have to draw this by hand, so we'll do the best that we can. Let's see here. So I'm going to just do a quick sketch. It won't be super duper accurate, but it'll serve our purposes. So if you were to have a graphing calculator or Desmos and you were graphing this guy, it would look something like this. So it'll start in the bottom here, and then it's going to run up to here, all the way up here, then it's going to curl back down through here, and then through here, something like this, right? And I asked you to find the x-intercepts. Well, okay, that's easy. Here's the x-intercepts, here's the x-intercept, here's the x-intercept. But the problem is, even though this is a quick sketch and you'll have a computer-generated graph when you do your practice, I don't know what, for example, I don't know what this x value is. Is it negative 2.5? Is it negative 2.7? Even though my sketch is a bit rough, I can't be 100% accurate. So the idea is you have to look for any x value that's easy to read. And judging by how horrible my graph is, I hope you guys can see that this is an x value that's easy to read. Well, we do what we did yesterday. I have an equation to solve, and I already know one particular answer. So, as we did yesterday, if you have an equation you want to solve and you already know one answer, just synthetically divide it out to make the problem smaller. So that's what we're going to do. We're going to synthetically divide out, in this case, x equals 1, from the problem 4, 0, negative 20, 16. Remember, we had to put the 0 here because we don't have an x squared in the problem. So let's go ahead and synthetically divide it out. So again, I just want to summarize that you would synthetically divide out that 1 because it was an x value that was easy to read. So it's that 4, negative 16, negative 16, 0. Right. Once I have it down to an x squared, remember this problem started with x cubed, so all these numbers begin with x squared, x, and a constant. My job is to solve the remaining equation. Since the instruction said find all rational zeros, find all the zeros, I need to set it equal to 0 and solve. Let's make the problem easy on ourselves. I notice everything has a 4 in it, so let's divide out 4. We get x squared plus x minus 4 equals 0. So the first thing I would try is solve it by factoring. But guess what? This guy isn't factorable. So since this guy isn't factorable, we turn to the quadratic formula. So we know that x equals negative b plus or minus the square root b squared minus 4ac all over 2a. So let's just plug everything in here. So we have an a equals 1, b equals 1, c equals negative 4. So I'm not doing anything fancy. It literally is just plug and chug. So b was 1, b was 1, a was 1, c was negative 4, 2 is 1. And then you go ahead and just do math. So it's negative 1 plus or minus the square root of 1 plus 16 over 2. Negative 1 plus or minus the square root of 17 over 2. Anytime you do the quadratic formula, you want to see if you can simplify the radical. In this particular instance, we can't. So that's it. There are our 3 answers. Our answers are x equals 1 that we saw from the graph, and x equals negative 1 plus or minus the square root of 17 over 2. And again, I said there are 3 answers because this plus or minus counts as 2 separate answers. And we expected them to have 3 answers because the biggest exponent was 3. Whatever the biggest exponent is, that's the number of answers you should have. Right? So that's pretty easy if I give you a graph, right? If I asked you to find the zeros of a function and you have the graph, you just read the x values. If the x values are hard to read, you find one that's easy to read, synthetically divide it out, and solve the rest. Well, of course, the question comes, what if I don't have a graph, right? Well, you do the synthetic division part, except since you don't know what right answer to pick, you're going to have to guess and check. But there is a theorem, there is a technique that allows us to narrow our guesses, because if we didn't have any choices, if we didn't have any thing to go on, we'd be guessing forever. This idea is called the rational zero theorem. And the rational zero theorem states this: if you have a polynomial, f of x equals a sub n, x to the n, plus so on and so on and so forth, plus a sub 1 x, plus a sub naught, has integer coefficients, then every rational zero of f has the following form. X equals P over Q. Now you're probably wondering, what in the world is P and what in the world is Q? P is a factor of a sub naught, the constant, the very last number. Q will be a factor of a sub n, the leading coefficient, the very first number. But it's important that a sub naught and a sub n do not share any common factor. This theorem sounds confusing and complicated just reading the definition, but once you get into the actual finding of it, it's actually a pretty nice and easy way to write a list of possible rational zeros. Do note that this theorem does not find it for you. It just gives you a list of possibilities. So to find that list of possibilities, you basically have 3 steps. You want to find all the factors of the constant, which is the last number. You want to find all the factors of the leading coefficient, first number. Once you have the 2 lists above, you're going to place all the factors of the constant over all the factors of the leading coefficient. We also want to include plus or minus for the entire list. So for example, if I ask you to make a list, but you do not need to solve, make a list of all possible rational zeros of f of x equals 6x cubed minus 3x squares plus 12. Right. So I'm not going to give you this guy's graph, and I'm asking you, hey, what are the list of all possible rational zeros? What are the list of all possible x-intercepts? Well, the first thing you have to remember is that your last number is P, your first number is Q. So let's go ahead and make the list. So step 1, as described in the above, I'm going to find all the factors of the last number. So, okay, so the P number is 12. So we're going to do what we did when we did pairwise factoring, right? I always like to start with 1 in the number and then increase from 2, 3, and so on and so forth. So you got 1 and 12, 2 and 6, 3 and 4. I think that's the entire list. Step 2, find all the Q numbers, right? So we got Q is 6. 1 and 6, I always start with 1 in the number. 2 and 3, and that's about it. So now here's the important step, step 3. You're making the list. I like to do this systematically. I always include the plus or minus. I like to take every single P number and divide it one at a time and divide it by all of the Q numbers at once. So for example, we're going to start with, I don't know, let's start with Q equals 1 here, right? So every single P number will be divided by Q equals 1. So let's go ahead and do this. What is 1 divided by 1? Well, of course, that's 1, plus or minus. What is 2 divided by 1? Well, of course, that's 2. What is 3 divided by 1? Of course, that's 3. What is 4 divided by 1? 4, 6, 12. I think that part was pretty easy. Do you guys agree that we went through the full cycle of all the p-values by dividing it by 1? So next, I'm done with 1, right? Go on to 2. So rinse and repeat. Divide all of these numbers by 2. So we have 1 divided by 2. Move on to 2. Now I don't have to write down 2 divided by 2 because 2 divided by 2 reduces to 1, which I've already written. So the idea is if you can reduce your fraction, you don't need to write it down. So move on to 3. 3 divided by 2 I can't reduce, so I'm going to write it down. Move on to 4. 4 divided by 2 I can reduce, so I'm going to skip it. Move on to 6. 6 divided by 2 I can reduce, so I'm going to skip it. 12 divided by 2 I can reduce, I'm going to skip it. So I'm done with the 2's, move on to the 3's. We're going to divide all the P numbers by 3's. So let's rinse and repeat. 1 divided by 3, put the plus or minus. I can't reduce it, so I'll write it down. 2 divided by 3, can't reduce it, so I'll go ahead and write it down. 3 divided by 3, you can reduce, so you skip it. 4 divided by 3, 6 divided by 3, you can reduce it, so I'm going to skip it. 12 divided by 3, you can reduce, so I'm going to skip it. Last but not least, divide everything by 6. So start from the beginning. 1 divided by 6, you can't reduce, so go ahead and write it down. 2 divided by 6, you can reduce, so I'm going to skip it. 3 divided by 6, I'm going to skip. 4 divided by 6, 6 divided by 6, 12 divided by 6. All of those can reduce, so I'm going to skip it. This is the entire list of possible rational zeros. Right. We're not going to do anything with this yet, but I want us to make sure we are okay with writing this list first before we move on. So if you want to test yourself, we're going to do the same exercise, just making the list. We're not solving. We're going to do the next exercise with a couple of them. I don't know, test yourself, pause the video, try your own, and check your answers at the end, or follow along if you're still trying to get the hang of it. So same instructions, find the list of all possible rational zeros. So again, we're only generating the list, we're not solving. 8x to the 4 plus 4x cubed minus 10x plus 15. This is our p-value, this is our q-value. So p of 15, that's 1 and 15, 3 and 5, I think that's it. Q-value of 8, that's 1 and 8, 2 and 4, and that's about it. So we can make our list. First things first, divide everything by 1. So that's plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. So all I did was I divided all of these numbers by 1, which anything divided by 1 is itself. Now I'm going to move on to 2. Divide everything by 2, and if there's anything you can reduce, you skip it. So 1 divided by 2, 3 divided by 2, 5 divided by 2, 15 divided by 2. Move on to the 4. Divide everything by 4. 1 divided by 4, 3 divided by 4, 5 divided by 4, 15 divided by 4. Move on to the 8. Divide everything by 8. 1 divided by 8, 3 divided by 8, 5 divided by 8, 15 divided by 8. So in this case, we had to write down everything because nothing reduced, so that's the entire list of all possible rational zeros. If this function had a rational zero, I'm not saying it does, but if it did, it's guaranteed to be in this list of numbers here. Let's just do one more of this list writing before we actually go ahead and solve, right? So again, if you're good, feel free to skip this example. If you want to test yourself, pause the video, do it yourself, and then check your answers. So find the list of all possible rational zeros of 4x to the 5 plus 3x cubes minus 2x minus 14. So the p-value is the last, the q-value is the first. So p-value of 14, that's 1 and 14, 2 and 7, and I think that's about it. Q-value of 4, that's 1 and 4, 2 and 2, and I don't really need to write it twice, but I did. So let's make our list. First things first, divide everything by 1. So divide all the p numbers by 1. Of course, when you divide by 1, it's just itself. So you have plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. Done with 1. Divide everything by 2. And if it can reduce, you go ahead and skip it. So dividing 1 by 2 gives you 1/2. 2 divided by 2 can reduce, so I'll skip it. 7 divided by 2. And then 14 divided by 2 can reduce, so I'll skip it. So I'm done with the 2's here. I don't need to do this 2 because it's the same, so now divide everything by 4. So divide all these numbers by 4. Plus or minus 1 over 4. 2 over 4 I can skip because you can reduce it. You get plus or minus 7 over 4. And then 14 over 4 I can skip it because you can reduce it. This is your entire list. So where is this list helpful is if I ask you to solve an equation and I don't give you a graph and it's not groupable, right? Normally if you can solve things with factor by grouping, you go ahead and do it. But if it's not groupable, you just go ahead and solve it like normal. So let's go ahead and just do a quick example here. Say I ask you to find all zeros of f of x equals 3x cubes plus 19x squares plus 4x minus 12. So I should notice it's 4 pieces, so you should always try factor by grouping first. But in this case, it's not going to work. So also, they're not going to tell you a hint. Hey, x equals 5 is a factor. Hey, x minus 3 is a factor. They don't give you any extra information, so you're sort of like left hanging in the wind. If you're ever asked to solve a polynomial and you don't have a graph, you don't have any extra information, and it's not groupable, you have to resort to your P's and Q's. So let's go ahead and make the list for this example here. So the same thing, the same previous 3 examples, go through the motions. My p-value is 12, so that's 1 and 12, 2 and 6, 3 and 4. My q-value is 3, 1 and 3. So you make your list. Let's divide everything by 1. So all these numbers you divide by 1, which is just itself, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. I'm done with 1. Now let's divide everything by 3. Remember, you only need to write it down if you cannot reduce it. If you can, skip it. So divide 1 by 3, I go ahead and write it down. Divide 2 by 3, go ahead and write it down. 3 by 3 I can skip because that can reduce. Dividing 4 by 3, I go ahead and write it down. 6 divided by 3, I can reduce it, so I'll skip it. And 12 divided by 3 can reduce, so I will skip it. So this is the entire list. Now here comes the time to guess and check. Now this would probably be best done on scratch paper or on a whiteboard that you can erase easily. But your job is to do synthetic division with this problem here. 3, 19, 4, negative 12. And you have to put a number out here. Now, it is a guessing game, so you have to go fishing, but you not out of luck. These are the pool of numbers you can guess. So if a number is not in this list, positive or negative, you don't guess it, right? So you can guess anything you want. You can check 1 and do the motions. Your goal is to get a 0 as a remainder, because if you get a 0 as a remainder, that'll tell you that it is a factor. So just to show you what I mean is I'm going to guess something that's wrong, and then we'll guess something that's right. So I'm going to guess randomly x equals 1. Maybe I think that's the answer. So we have 3. So I wouldn't copy this. Oh, I mean, copy down if you want. It's good to copy down wrong things. 3, 22, 22, 26, 26, and 14. So because this is not 0, x equals 1 is not an answer. So what do? You just got to try something else. So that's basically it. It's easy and hard at the same time. Easy in that you only have to guess a certain amount of numbers. It's hard in that if you suck at guessing, you might have to do this many, many, many times. That's why scratch paper or whiteboard would be good. So let's check -1. I don't know. I have a feeling that -1 might be the ticket. So we have 3, 19, 4, -12. We have 3, -3 here. 16, -16. That's going to give me a -12, +12, and lo and behold, I get a 0. This is what I want. So I know that x equals -1 is a good answer. I'm not going to forget about it. But I want to solve for all of it, so you got to solve the remaining polynomial. Our problem started with x cubes, so this is an x squared, x constant. Your job is to solve 3x squares plus 16x minus 12 equals 0. And you go ahead and solve it however you want. Solve it by factor by grouping, solve it by factoring, solve it by completing the square, or the quadratic formula, right? Some of you guys might like to do the factoring when you take the first number times the last number. Go ahead and do that. I'm just going to go ahead and do the guess and check method. So I know it's going to be 3x on an x. And if I guess properly, it's going to be a 3x minus 2 and a plus 6. So there we go. We get 3x minus 2 equals 0. X plus 6 equals 0. So x equals 2/3. X equals -6. But wait a minute, that's only 2 answers. I should have 3 answers here. Don't forget the -1 that you correctly guessed. So there are our 3 answers. So that's basically the main point of this lesson here, is that it's going to be just like yesterday where you're going to be solving polynomials, but in this case we're taking away the training wheels. I'm not going to give you a 0. I'm not going to give you a factor. If I do not give you a graph, you have to do this rational zero theorem. You have to do this P's and Q's to come up with the list so you can guess and check on your own. It takes a while to get used to, but once you get in the hang of it, it should be pretty simple and straightforward. Good luck.